The Great Exhibition of 1851 required a building covering 772,784 square feet to be constructed in Hyde Park within 10 months, operated for 6 months, then completely removed to restore the Royal Parkland. Traditional masonry construction would take years and leave permanent foundations, making parliamentary approval impossible. Joseph Paxton, a greenhouse designer, proposed a prefabricated system using cast iron, wrought iron, and glass assembled on site from mass-produced components. The proposal was accepted in July 1850, with the exhibition opening scheduled for May 1851. This left no margin for redesign. The structure would depend entirely on manufacturing precision, dimensional coordination across suppliers, and assembly sequencing that could absorb no delays. The following breakdown decodes the 10 critical engineering systems that made the Crystal Palace possible and the unresolved risks embedded in each. Fact 1. The entire structure was designed on a fixed 24-foot module that governed every horizontal dimension. This was not aesthetic, but a manufacturing constraint. Custom components could not be produced in the required time frame. The ground plan measured 1,848 feet long and 456 feet wide, subdivided into 77 bays lengthwise and 19 bays crosswise. By standardizing every structural bay, Paxton converted the project into a mass production problem where multiple foundries and workshops could produce identical components without waiting for custom drawings. The grid eliminated most dimensional variation, but it transferred all risk to tolerance accumulation. Any deviation in one component would propagate across the entire bay, and errors would only become visible during assembly. Fact 2. Cast iron columns carried all vertical loads, and their maximum length was governed by foundry casting limits rather than structural requirements. Columns were cast vertically in sand molds, with molten iron poured from the top and cooled from outside inward. Longer columns required larger metal volumes, increasing cooling time and the probability of internal voids or cracks. Foundries could reliably produce hollow columns up to 20 feet in a single piece. Paxton specified 3 standard heights: 20 feet 4 inches for ground level, 16 feet for galleries, and shorter for upper tiers. Each column was cast with integral sockets at the top to receive beams, eliminating field drilling. Multiple foundries across England produced columns simultaneously using identical patterns, but dimensional consistency between suppliers became critical. Even small differences in socket depth would prevent beams from seating correctly. Fact 3. Horizontal beams used wrought iron rather than cast iron, driven by tension performance under bending loads. Cast iron resists compression but fractures under tensile stress due to brittleness. Wrought iron contains fibrous slag inclusions that arrest crack propagation and provide ductility in tension. Each beam was an I-section rolled to standard dimensions and cut to the 24-foot module. Beams rested in column sockets, transferring load through direct bearing rather than bolted joints. This simplified assembly but required precise alignment. If a column was out of plumb, the beam would not seat flat, creating eccentric loading and potential cracking. Foundations were isolated concrete pads placed under each column, reducing excavation and allowing full removal after the exhibition. However, each pad had to be positioned with absolute accuracy before assembly began, with no method to correct foundation errors once columns were erected. Fact 4. Glass panes were constrained by the cylinder manufacturing process. Glass was produced by blowing molten glass into a cylinder, cutting it lengthwise, and reheating to flatten into sheets. The process had physical limits. Cylinders larger than 5 feet in diameter became unmanageable, and flattening larger sheets introduced thermal stress, causing cracking. The practical maximum for architectural glass in 1850 was 49 inches by 10 inches. Paxton's roof had to subdivide each 24-foot bay into glazing units matching this size. The building used approximately 293,000 panes, nearly all interchangeable. This allowed factories to run continuously without retooling, but the iron framework had to be fabricated to tolerances matching glass dimensions exactly. Any warping or misalignment would create gaps or force fitting that could crack panes during installation. Fact 5. The ridge and furrow roof profile provided stiffness through folded geometry while channeling water into integrated gutters. A flat glass roof spanning 24 feet would require heavy framing to resist wind uplift and prevent deflection. By folding the roof into alternating ridges and valleys spaced 8 feet apart, Paxton created a corrugated surface where each angled plane braced the adjacent plane. The angled surfaces directed rainwater into the furrows. Each furrow incorporated a cast iron gutter running the full building length, and these gutters were not merely drainage channels, but primary structural members. The gutter cross-section was a trough, with flanges connecting to glazing bars above and beams below, creating a composite structure where the gutter resisted roof loads while carrying water. Fact 6. The gutter beam connection transferred roof loads into the column grid, but had to allow thermal expansion without binding or cracking the cast iron. Cast iron expands approximately 12 millionths of an inch per degree Fahrenheit. A gutter running 1,848 feet could expand nearly 2 inches over a temperature swing from night to day. If rigidly fixed, thermal expansion would generate forces that could crack the cast iron. Paxton used a sliding connection where gutter flanges rested on beams but were not bolted, allowing longitudinal movement while maintaining vertical load transfer. This created a risk. The connection had no tensile capacity, meaning wind uplift could lift gutters off supports. Tie rods connected the roof to the column grid at intervals, anchoring against negative pressure. Fact 7. On-site assembly followed strict sequencing that allowed work to proceed without waiting for completion of prior zones. Foundation pads were laid out in the 24-foot grid and leveled using wooden stakes and string lines, a method with inherent error that could accumulate across 1,848 feet. Columns were erected bay by bay using hand-operated shear legs. Once set, beams were lowered into sockets. Roof trusses followed, then ridge and furrow framing, finally glass. The assembly advanced as a rolling front with multiple crews working simultaneously. This parallelization compressed the schedule but required precise coordination. If one crew fell behind, downstream crews would stall. Errors in early bays could not be corrected without disassembling completed sections. Any manufacturing delay would cascade through the entire schedule, and the exhibition opening date was fixed. Fact 8. The compressed schedule left no margin for design iteration or material testing. Every component was fabricated based on calculations with no experimental validation. Paxton used beam theory and column buckling formulas from engineering handbooks, but these were empirical approximations. Cast iron columns were sized based on estimated loads and typical safety factors, but no samples were tested under load. Wrought iron beams were designed using allowable stress values from prior construction, but no load tests were performed on the specific sections. Glass was assumed to resist wind pressure based on greenhouse experience, but the Crystal Palace roof was far larger than any greenhouse. The gutters serving as structural members had no precedent. Construction proceeded on the assumption that calculations were conservative enough to absorb unknowns. Fact 9. Fire resistance was not part of the structural design because the building was temporary, but the combination of cast iron, wrought iron, and glass created specific failure modes under heat. Cast iron does not burn but loses strength rapidly above 800 degrees Fahrenheit and fractures suddenly when heated unevenly due to brittleness. Wrought iron retains more ductility, but will sag and deform under load as temperature rises. Glass cracks when exposed to rapid temperature gradients. The Crystal Palace had no fire suppression, no compartmentalization, and no fire-resistant coatings. Internal spaces used gas lighting, timber display structures, and flammable materials including fabric drapery and wooden flooring. A fire starting in exhibition contents would rapidly heat the iron framework. Cast iron columns would crack if heated unevenly. Wrought iron beams would sag, pulling connections out of column sockets. The glass roof would shatter from thermal shock. Fact 10. The Crystal Palace was disassembled after the exhibition and re-erected in Sydenham in South London with modifications including enclosed galleries, additional floors, and permanent foundations, all of which increased fire load and compartmentalized spaces that trapped heat. The structure operated as a public exhibition space for 82 years. On November 30th, 1936, a fire started in an office around 7 p.m. and spread through timber partitions into the main structure. Cast iron columns fractured as they were heated unevenly by flames, losing load-carrying capacity and collapsing in sequence. Wrought iron beams sagged and pulled free from connections, allowing entire roof sections to fall. The glass roof shattered, feeding the fire with oxygen. The fire consumed the structure in hours. The failure was not an accident, but the realization of a risk embedded in the original material system. Cast iron and wrought iron in an open structure with combustible contents had no inherent fire resistance, and the temporary nature of the 1851 design meant fire performance was never part of the engineering specification. The Crystal Palace functioned as intended for the 1851 exhibition, but its engineering constraints and material risks never disappeared. If this kind of mechanical breakdown interests you, follow Grandeur Decoded for more engineering deep dives into the systems behind iconic structures.